All right, let's get started. So today, I'm dedicating this entire lecture to just introducing a brand new function, and a function which we will then use forever thereafter. So we haven't used it at all up until this point, and some of you have probably seen this function before, but today we're going to formally define it. So if you've seen this function before, and you know what this function is, don't spoil it for the rest of the class, okay? So we know that if n is an integer which is not equal to 1, or let's say not equal to -1, then the indefinite integral of x to the n dx is x to the n plus 1 over n plus 1 plus c, right? And the reason why n can't be equal to -1 is evident here because we'd be dividing by 0. What a disaster that would be, right? Okay. So n can't be equal to -1. And what we're then forced to ask ourselves is, well, what happens if x is equal to -1? So what if x is equal to -1, right? Okay. So if x is equal to -1, as far as this class is concerned, I know some of you might, again, know the answer, but as far as we're concerned, in this class, we don't have an elementary antiderivative for 1 over x, right? Because that's what happens when x is equal to 1. So we don't have, there is no elementary antiderivative for 1 over x. So what we're going to do is we're going to define it to be. Oh, yes. Thank you for n equals 1. Thank you. So yeah, let's define it. So let f. Now, of course, we run into trouble at 0, and we want our domain to make sense. So we're just going to restrict our attention to 0 to infinity. And this is just going to be, this is the function we're talking about, 1 over x. And define a new function to be its antiderivative. Okay, and you could start anywhere. Convention is very much usually to start at 1. Okay, but we're going to define this function right here. Right, and the FTC, which one? FTC1 tells us the derivative of big L is 1 over x, right? No problem. So with this definition in mind, we immediately have a bunch of very easy results that we can prove. So proposition the function L satisfies. All right, so 1, the derivative is 1 over x. Okay, and I'm actually not going to prove this because all of these results are immediate. Okay, but let's just discuss why they're immediate. So this is by FTC. Right, the derivative of the integral is whatever the integrand is. So that's number 1. Number 2, L is strictly increasing. Okay, why is that true? Like without needing to prove anything. Or if you were to prove it, what would you do? Any guesses? Right. Okay, yeah, so there's a couple things here. So Summer, you're very close. You want that 1 over x is positive, right? And Nicole, exactly. So by 1, the derivative is positive, right? So yeah. L prime of x equals 1 over x is greater than 0. Because let's think about, right, what the domain is. And Adam, I guess what you would want to say is maybe like the integrand that you're summing over is always positive, right? So you'd always keep adding stuff up. And that's absolutely true. That's actually kind of a nice thing that we didn't comment about in the fundamental theorem of calculus, is that if the function you're integrating is always positive, then your integral function must be strictly increasing, right? Because you're always adding on, you're like summing up more and more positive areas. So you can think about it like that as well, absolutely. If you were to actually prove it though, you probably want to use like the derivative thing, right? But yeah, no, that's a good kind of like intuition behind that. Okay, L of 1 is equal to 0. All right, that's just basically by definition, right? Because if you plug 1 in, you're going to integrate from 1 to 1, so nothing really happens. For L of x is less than 0 if x is less than 1, and L of x is greater than 0 if x is greater than 1, right? And that's just by 2 and 3. Right, so the function is strictly increasing. You know it's equal to 0 at some point. So if you're strictly increasing and you go through 0, well, you had to be beneath 0 before it, and you had to be bigger than 0 after it, right? So you're done. Nothing to do there. Okay, so like I said, we're not going to prove these because these are kind of immediate, but they're nice to write down. They're nice to have in front of you because we're going to use these. And so now here is a real thing. Okay. And let's see how I want to state this. If L, or maybe I should specify an X. Yeah. If L is the function above, then 1. All right, now here's where stuff gets interesting. Okay, so L satisfies this weird property that if you take any two numbers and you evaluate L on their product, that's the same thing as if you had distributed them and then just added them up. L of 1 over x is equal to negative L of x. And 3, L of x to the, let's call that q, is q L of x for all x in 0 infinity and q in the rationals. Okay, and at this point, even if you don't know what L is, you're probably being like, wait a second, I've seen a function which does those things before, and you probably are starting to get a guess of what this function is. All right. Okay, but we got to prove these things. So for those of you who know what this function is ahead of time, these are just properties that you get immediately, right? That's not how we're defining this function. So, we have to actually prove these things. And the proofs are surprisingly easy. Okay, so for number 1, let's fix a y right out of the bat. So fix y in 0 infinity. Okay, and we're going to let x still be a variable. So we're going to differentiate L of x, y, right? Almost like we're differentiating L of 2x or L of 10x or something like that, right? Like we're just using basically the chain rule to do it. So if we do that, not comma, that's just x times y. Okay, what do we get? So using the chain rule, y L prime x y like that, right? But we said we know what L prime is, right? It was number 1 in the previous thing, or by the fundamental theorem of calculus, it's just 1 over x. So I get 1 over x times y. And the y's cancel out. Y is not 0, so this is okay. That's 1 over x. And here's the weird thing. That's the exact same thing as just the derivative of Lx. So the y doesn't seem to matter, right? So when you differentiate Lxy for any y, we just get the same thing as the derivative of L of x. We know that antiderivative, so L of x, y is an antiderivative of 1 over x, but so is L of x. And we know that those are unique up to additive constants, right? So L of xy is L of x plus some constant. Now, if we want to figure out what that constant is, we just choose a clever value of x. Let's say maybe x is equal to 1. Then we get L of y is L of 1 plus c. But we said above L of 1 is 0, right? And there we go. The constant is c, or the constant is L of y. And we're done. All right, so again, if you think about differentiating now the right-hand side, like if you know that this identity is true and you differentiate the right-hand side with respect to x, the L of y is just a constant, which is why we just got out the derivative of L of x, right? Is that if this identity is true, the L of y just disappears because it becomes a constant. Yeah. It's okay. There are still short proofs in our future. They're not all gone. Okay, so L of 1 over x is negative L of x. For this one, what we're going to do is note that 0 is equal to L of 1. And what I'm just going to do is I'm going to write 1 in a special way. So I'm going to write it as L of x times 1 over x, right? Now I'm going to use the property above, which allows me to split these up. And if I solve that thing for L of 1 over x, then I'm done. All right, that's a really short proof. Okay, number 3. Now, number 3 takes a little bit of time just because we have to bootstrap up. So what we're going to do is we're first going to prove it, right? Like, what are we trying to prove? So we want to show that basically we can pull the exponent out and down, and that is true for any rational. We're going to bootstrap it, though. We're going to start by proving it's true for the naturals. Then we're going to prove it's true for the integers. Then we're going to prove it's true for the rationals, right? We're going to build up to it. So let's say if n is an n, so if n is a natural number, right, then, and in theory you could do this one, you probably should do this one by induction, but I'll be damned if I care. Right? I'm not going to write it all out that many times just so that we can do it by induction. Right? So what that means is, we multiply x together n times because that's actually what exponentiation means in this case. And again, right, like technically we know this is going to be true. We really should do this by induction, but no. Right? So there we've proven the result now for a natural number. Now I want to extend it to, and it's certainly true. Is 0 a natural number here? I guess I'm saying no. If n is equal to 0, it's trivially true, right? We've got L of x to the 0 equals L of 1, which is equal to 0, which is equal to 0 times L of x. Okay, so yeah, so now let's go and let's do it for the negative naturals as well. If we do it for the negative naturals, then we've done it for all the integers. Moreover, L of x to the negative n, right? So instead of saying let it be an arbitrary integer, I'm just going to do all the integers just by doing the positive naturals, the negative naturals, and 0, which is the same thing. And you can see what's going to happen. So this is, again, just 1 over x times 1 over x a bunch of times. And again, we're going to split that up, 1 over x, 1 over x. By part 2, these are just negative L of x's. And we do that n times. So that gives us negative n L of x, right? Okay. So it's true for every integer. So the result is true for all n in Z. Okay, so now we have to do rationals, right? And so this is a common trick, and we've kind of, I think, I don't remember if I made you do this exercise where we play with this before, But this is always how it goes. Anytime you're trying to prove something, holds for all rationals, prove it for the naturals, prove it for the integers, build up and bootstrap. And you're going to do basically exactly like the trick that I'm going to use for the rationals is the trick you always use. Okay, so if you haven't seen this one before, here it is. So I shouldn't have called the rational q because I kind of want to use that as my denominator. I guess I'll have to name it something else. So let q be a rational number, a over b in z. Okay. All right, so what I'm going to do now is the following. So we know of x to the a is a L of x, right? Because a is just a natural, or a is an integer, right? Like we don't care, the rational number is a divided by b, but a itself is just still an integer, so we're not doing anything tricky here. We've already proven this is true. But the other thing, a is equal to b times q. Like that, right? Like if we take this thing right here and we solve that for a, we get a is b times q. So a is also equal to b times q. And how do I want to do this? Oh, sorry, this should be an L. And the way I'm going to write this is L of x to the q to the power of b, like that. Again, b here is a natural number or an integer if you want, so we can take it down like that. And now what I'm going to do is I'm going to take this thing and solve for lxq, right? Because that's what I'm trying to do. And that is exactly QL of x. Right? Now it turns out this result is true for every real number. So if your exponent is any real number, that's okay. But we, again, haven't even really defined what it means to raise a number to a real power. So we don't even know what that means. So we can't really talk about that in this context, but it will be true. Once we figure out what it means to raise a number to a real number to a real number, this will also be true for real numbers. Okay. All right, and there's one more thing that we need to prove before L is just a placeholder here. I'm going to tell you how mathematicians actually denote L in a second, but there is one more thing that we need to prove. Oh, that's not the right color. And this is the thing that you're going to find really useful tonight. Okay, so there is a unique number called Euler's number and denoted by little e, such that L of e is equal to 1. Oh, sorry, yeah, that should be Q. Man, I'm making lots of silly mistakes today. Okay. And if what is this deceptive function, if you still haven't gotten it, this should be a big hint as to what this function is, right? So we need to prove that this number exists. Now, we're not going to get a bearing on this number. We're going to have no idea what this number is, but we just need to prove that it exists. And I love this proof because this proof is just so remarkably, I don't want to say clever. It's just like such an unexpected use of integrals. This is a really cool example, okay? So what do we need to do? We know that L of 1 is 0. Or maybe let's start with it. We know L is continuous. by the FTC, right? L is that integral function of something that we know is continuous. So actually, we know that L is differentiable, but L is continuous by the FTC. Moreover, we know that L of 1 is 0. Okay, so if we can find some number, okay, we know it's injective. That's certainly true, Adam. So we're going to use the fact that it's injective. That's the uniqueness part. Injectivity is going to give us uniqueness. We haven't proved surjective, and that's going to be the tough part. But it turns out we don't actually need to know that the function is surjective, because here's the tricky thing, right? If we go back up here, I'll go back to that in a second. If we go back up here and we look at the definition of L, yeah, exactly. It's going to be an intermediate value theorem proof. We don't know that this function actually could add up to become an arbitrarily large number, right? It turns out it does. It turns out this function is surjective, but we don't actually know that, right? So like if especially 1 over x, so for example, if I change this number to 1 over x squared, right? Or if I did 1 over t squared dt, this function wouldn't be surjective anymore. And, like why not? And in fact, this function grows so slowly, right? Because 1 over t gets really, really small. So as you add them all up, they do get really, really big. They get arbitrarily big, but it can take forever for them to get to a big size, right? So even if you were to graph this function, it's not really evident that it's totally surjective, right? So yeah, there's a little bit of weird trickiness there. So exactly, let's intermediate value theorem this. We know that L of 1 is 0. All we need to do is find another value such that L of that number is bigger than 1, right? So if we can find some n in R such that L of n is greater than 1, then by the intermediate value theorem, there will be something that makes it equal to 1, right? E will exist. Okay, and then as Adam was saying, right, we know that the function is strictly increasing, therefore it's injective, and therefore that can be the only value for which it's true. Moreover, L is strictly increasing, hence injective, giving uniqueness. Okay, so all we have to do is find some number that makes the function bigger than 1, but we said the function is strictly increasing. So probably if you just chose n to be really, really big and computed what L of n is, you could do it. The problem is that L, by virtue of how we've defined it, doesn't have an elementary antiderivative. So how the hell are we going to compute this thing, right? Because it doesn't have an elementary antiderivative. We can't use the fundamental theorem of calculus in order to evaluate this integral. But the point is that we don't need to figure out exactly what it is. We just need to prove it's bigger than 1, right? So let's prove it's bigger than 1. And it turns out, so I'm going to choose the one that I think is the easiest, basically the first number that works. I went ahead and I kind of computed it ahead of time. So I'm going to choose the first number that works, and the answer I'm going to choose n is equal to 4. So claim L of 4 is greater than 1. Okay. All right, let's prove this. And now here is here is where it is a little bit slick. So what I'm going to do is consider the following partition of 1, 4. Right? And the reason that I'm doing this, right, like let's think about, maybe here, let me put this up here. What are we trying to show? L of 4 is the integral from 1 to 4, right? Let's not lose sight of what L is defined to be. L of 4 is the integral from 1 to 4. I need to prove that that integral is bigger than 1. So what I'm going to do is I'm actually going to take a partition of the interval 1 to 4, and I'm going to choose just the dumbest partition I can think of. And I'm just going to take like this trivial one that just takes, every single integer in that range. Now, 1 over x is a decreasing function, right? Since f of x equals 1 over x is decreasing, and is in fact continuous, but we're not as worried about that. That means that when I compute the lower sum here, that the lower sum will always be given by the right endpoint, right? So I'm going to get the right endpoint of the interval multiplied by the interval. But the interval length is just 1. So this gives me 1/2 plus 1/3 plus 1/4. Does everyone agree? All right, so let's say this is 1, 2, 3, 4. So I'm just computing, what is it? Like this. That sum right there. Okay, and what is that number? Hopefully I've done this correctly. So common denominator is 12, so that would be 6 and 4 and 3, so that's 13 twelfths. Right? So does that do it though? The answer is yes, because we know that the lower sum is always an under approximation, right? The integral itself, which we know exists, will always be bigger than the lower sum. So this number itself is bigger than 1. And so the integral, or L of 4, which is the integral from 1 to 4, is going to be greater than or equal to LFP, which is itself greater than 1. And so we're done. Yeah, right? And of course, you could have chosen something else if you wanted to. Like if you chose finer partition, right? So maybe you did like 1, 1.5, 2, 2.5, 3, 3.5, 4, something like that, you would get an even better approximation. But then you have to add more fractions, and I don't want to add more fractions, right? As far as I'm concerned, adding a half plus a third plus a quarter was already hard enough. So, we got that, and it wasn't too bad, but there you go. All right. So mathematically, this function is called the logarithm. So mathematically, we call L the logarithm. Some people will say the natural logarithm. And denote it as log x. Okay. Now, a word on notation. I should explicitly write this down. Some people are going to get upset here. Some people do write log instead, right? In fact, most of you probably, as you were, the first time you learned logarithms, learned this. And even though we haven't learned about what different bases mean, let me just say, students I know always get upset when they see log. They're like, no, log means log base 10. No, that's nonsense. The log never means log base 10. Log means log base e, always. All right. So when mathematicians write log, we don't mean log base 10, we mean log base e, always. That is the only logarithm function. All right. There are no other logarithms. That is the logarithm. When you do have different bases, because of course sometimes it happens, when you do have different bases, those are special. Those are special cases. Those are weird. This is the only thing that shows up organically in real life. Your calculator has a stupid log base 10 button. That almost never is used in real life, right? There might be a couple of occasions where the random engineer might use that and use log base 10. But in terms of all real life applications, everything, when the logarithm shows up, it's almost always log base e. So why would we give it a special notation? It is the logarithm, right? So for this class, if you see log, it's log base e. It's not log base 10, it's log base e, okay? Don't get confused there, because otherwise it's gonna hurt you. Mathematicians always mean log base e. We haven't even talked about in this class what base e means, right? And because in order to do that, we have to define what an exponential is, right? So that's the next step. Okay. So by the inverse function theorem, right? L prime of x is never equal to 0. And is C1 everywhere. So you proved, right, on a test, probably, yeah, why is log not the universal symbol for log base e? That's a good question. It's probably historical, right? Because historically, we did work in base 10, and historically, people did invent exponentiation first. Like, think about what we're doing here. Yeah, and yeah, physicists is a good one. Engineers is a good one as well. Historically, exponentiation came first. The logarithm was the inverse of exponentiation, right? And what are the natural things what are the natural bases that you do exponentiation in? 2 and 10, right? And then e. So historically, the first base, the natural base that everyone used was like 2 and 10, right? Yeah, sure. Yeah, log base 10 for pH, sure. And yeah, as a general rule, yeah, so log base 10 basically came first. Log base 2 is also super important if you're doing like computer science and stuff, right? But then the mathematician said, okay, something is fishy here, right? And we don't know how, like basically the mathematician said, okay, if we want to be rigorous about how to define things, we're actually going to start with the logarithm and then use that to define exponentiation. So sometimes historically, what comes first mathematically gets reversed, or mathematically we approach it in a different way, which breaks convention between mathematics and physics, or mathematics and engineering, mathematics and chemistry, whatever the case might be, right? So same thing, right? With the definition, for example, of a prime number. I don't know if you guys have seen like the good definition of a prime number yet. So most people, when you say what is a prime, they say it's a number whose only divisors are one in itself, right? Or it has two distinct divisors, one in itself. But there's a better definition of a prime, which is a number p is prime if whenever p divides a product, it must divide one of the things in that product, right? And if for those of you in 102, you've probably seen this, right? It's not stated as an alternate definition of the prime, right? It's an if and only if. P is prime if and only if whenever p divides a, b, p divides a, or p divides b. Turns out that's the better definition of a prime. And yeah, we kind of like retcon what the math definition is. So for that reason, math is maybe being a little bit disingenuous here, because historically log probably was log base 10, but as life and science and physics and everything evolves, we've learned no, log base e is obviously the natural thing to do. That's why it's called the natural logarithm, right? And the natural exponential. And so we've sort of retconned the notation and said log is log base e. That being said, if you are going to do this and you are writing science papers, you have to be really specific about that and declare it at the beginning of your paper or something so you don't confuse people, right? Okay, so by the inverse function theorem, L prime of x, L is a C1 function, right? Certainly differentiable, and its derivative, 1 over x, is continuous on its domain. So it's a C1 function, and its derivative is never 0. So by what you proved, I think, in term test 3, maybe, or term test 2, whichever one it is, it has an inverse. It has a C1 inverse everywhere. So there is an inverse function. I guess I should say log now. Log prime feels weird to write. So there is a global inverse, maybe I should say. Which we call exp. And because it's an inverse, right, it's just going to flip around the domain and codomain. And that's the definition of the exponential for our purposes, right? The definition of the exponential is it is the inverse to the logarithm. which again is kind of backwards than how this is done in, for everyone else and how you're actually taught logarithms and exponentials. Okay, let's very quickly do some properties of exp. I'm going to prove probably the first one, and then I'm going to leave the other two to you because they're just straightforward definitions. So number one, no, let's use exp now because that's what we're doing. In R. Okay, so, and again, this should in some sense be clear. It's reversing this rule for the logarithm, right? The logarithm is this rule in reverse. The exponential is the inverse function. So to some extent, we expect that to be true. And same thing with 2 and 3 here. So 2 is what do I want? All right, so we're getting the same sort of arguments, but in reverse. No, I use Q. Let's be consistent. Okay, so all three of these properties are just, again, I recommend that you give them a shot if you haven't, but they just follow from the properties of the logarithm because they effectively are, the logarithm properties, but sort of reverse for the inverse function. The only one that's a little bit, that has a little bit of a trick here is number one. So I'm going to prove number one for you, just so that you can see what the trick is. So, because if you need one to do 2 and 3. So the trick is to use the property of, is basically use the fact that these are inverses, right? So number one, we know that this is just equal to x plus y, right? Since log inverse is equal to x, right? But this thing on the right-hand side is also just log x plus log x y, right? And then log has this, right? Here's where we're going to use the special property of log. Since log, let me call this like WZ or something. Log W plus log Z. Okay, and why does this do it? Why is the fact that these two things are equal imply that their insides are equal? Yeah, it's strictly increasing. Inverse, I mean, there's a slightly better word here, but both, Yvonne and Nicole, you have the right thing. Well, okay, so we don't know it's surjective, but what part of bijection do we actually want here? Because we don't need surjectivity for this, right? We just need injectivity, right? Log is injective. And so, right, this is again kind of a nice, we're really seeing injectivity come into play, right? Like this is precisely the statement of injectivity, right? Since log is injective, these two things are equal, so their arguments must be equal, and we've used that to prove something. I think that's pretty nice. Okay, so yeah, I'm going to leave the other two as exercises for you. You can give those a shot. And then there's just one more proposition that I want. So proposition No, I'm using X. So the derivative of the exponential function is the exponential function, right? So proof. We're just going to use the inverse function theorem. So by the inverse function theorem, the derivative of the exponential function, that's the same thing as the derivative of log inverse, right? And by the inverse function theorem, we have this formula, which is 1 over log prime x of x. Log prime is just 1 over x, so that just gives us x of x, and we're done. Okay. So again, notationally, you can continue to write exp if you want, but notationally, exp x is e to the x, where e is Euler's number. And there's a little bit of, sophistry here. Like, we need to convince ourselves that this makes sense. Right? How did I get the a? Yeah. So yeah. So log prime of x equals 1 over x. So that means 1 over log prime of x is just the function x. Yeah. Okay. So notationally, this is what we're going to write. It does turn out e is Euler's. Maybe let me not do this right now. Let's actually cut this. Notationally, this is how we're going to write the exponent. Okay, and the fact that this will actually turn out to be exponentiation is something we'll have to convince ourselves of later. But this is often how this function is written instead. And then as well, so if a is some positive number, we're going to demand that a be positive, and x is in 0, infinity, we will write a to the x is e to the log a to the x, right? Or x log a. And this is actually now going to be the definition of this thing. Okay. Now all you have to do, and again, I'll leave this as an exercise for you, but I think hopefully we all believe it, even if you don't quite see why it's true yet, convince yourself that if a is, let's say, a natural number and x is rational, then this is the usual definition of exponentiation. Right? And it's going to be obvious. Like, I hope it's obvious why that's true, right? Because if I have a as a natural, I guess actually, do I need a to be? No, I don't even need it. It could be, let's just say a is in 0, infinity. Because again, right, we don't know how to exponentiate a real number power, but we do know how to exponentiate a rational number power. That's fine. So as long as x is a rational number, this should just boil down to exponentiation, and it does, precisely because e and log are inverses of one another, right? Because so in this case, we would get e to the x log a is e to the log a to the x. And again, I can do this precisely because x is rational. If x is real, we don't know that this is true yet, but x is rational, so I can do this. E and log are inverses of each other. So this gives us the classical definition of exponentiation, right? The great thing about this now, though, is that this definition here holds when x is a real number, right? And so this is how, for our purposes, we have defined this function. Up until now, we only knew how to do rational exponents, but now that we have the exponential and the logarithm, we can define it for real exponents. Okay, so this will be the definition of this for us.
May I ask a question?
Mm-hmm.
Like when you write e to the power of x log of a, well, you already have like real numbers. You see what I mean? Like,
sure,
x is a real number and x is an exponent there. So
no. Okay, hold on. Let me write it slightly differently so it's not an exponent. It's not an exponent though, right? We said e to the x is just notation.
Yeah, okay, now I got it.
Right. And the fact that later it will turn out to actually be e, like the same thing as exponentiation with the base being Euler's number. What I'm saying is here, like we know that the exponential function is defined, and it's defined for all real numbers, right? So instead of, to make it not be circular, the definition of the exponential is just that it's the inverse of the logarithm, right?
Yeah, and so is an integral, so we can do that. Okay, I got it.
Right. So yeah, it felt like me cheating, right? But it's just a matter of like, let's just, we have to remember this right now is just notation. It will turn out to be true later. Or even if we want, this is just like true by definition now, right? Like we've said that this is the correct generalization of, So let's see. So we said for every real number now, this is true, right? So this identity now is true for any positive real number a and any rational number x. So if we again let x be rational, then x log e is x, right? And we said, well, this should be the same thing as this with the base. So now these are in fact equal, right? With a rational exponent, not with a real exponent. And then we generalize to real exponents by using, let me put it in yellow now, by using this thing. Does that make sense? Everyone's good with that? Right? Like we know how to do r to the power of q. Like a real number to a rational power is fine. We know how to do that, but we don't know how to do real number to real power. And the way that we're going to do that is precisely with this definition. And this definition is okay, precisely because it isn't actually circular. These functions do exist for all real numbers. We've proven that. And then we're saying, oh, look, they agree with our usual notion. And so we're going to use this as the proper extension of what exponentiation should be. Yeah. Right. So it's actually like well defined now because we started with the integral. Yeah. Okay, everyone. So hopefully that makes sense and everyone's happy with that. Again, if you're a little bit unclear still about like why this does it for the reals, extends it to the reals and not for the rationals. Actually, I guess as well by this, remember this, where the heck is that theorem? This one. So this proposition number 3, which said that this is true for the rationals, by the definition now of, again, we've used the exponential and the logarithm to define x to a rational number. By this definition now, property 3 is true for all real numbers, right? because by this definition. So you might need to convince yourself of that, just like write it down and convince yourself. But yeah, that's true as well. Yeah, you'll see. Yeah, I can't clarify it more than that, but just like you'll see the question, you'll be like, okay, sure. Yeah, I promise you it'll become more clear once you see the test. Okay, everyone, that's going to finish us off for today. So good luck tonight. I'm sure you'll all do fine though. And yeah, study hard. Yes, yeah, you can. I don't think it's going to help you too much other than the particular technique that we might have used there to prove that E exists. But yeah, you can use this stuff if you want, definitely. Yeah, I don't see why not, Daniel. You should have a tutorial today. Like Paul is feeling better, if that's maybe what the question was. Yeah, no problem. All right, everyone. I will quote unquote see you tonight. Again, throw any last minute stuff on Piazza if you want, and I will try and check it out before the test starts. Okay. All right. Yeah, good luck. Have a good weekend too, because I won't see you. And ciao. See you then.